Think of the ultimate one-way street in the universe. A black hole is, by standard definition, technically impossible to destroy. Standard physics dictates that these gravitational wells swallow everything that crosses their path. Planets, entire stars, and even light itself fall in, and absolutely nothing escapes. These objects exist beyond theoretical equations. We have captured their physical reality on camera, mapping the glowing debris that outlines their immense central void. But at the extreme boundaries of theoretical physics, there is a strict rule. Nothing in the physical universe is permitted to last forever, not even these structures. You cannot blow it up. You cannot tear it apart. To conceptually dismantle one, you have to rely on a mechanism so microscopically small it barely exists, and then wait for the longest timeline imaginable. To see how a black hole eventually dies, we have to scale all the way down to a subatomic knife edge. This is the absolute border of the event horizon. Quantum mechanics shows us that empty space is never truly empty. It is a constantly bubbling ocean of energy. Within this ocean, pairs of virtual particles constantly pop into existence out of nothingness. They arrive as a matched set, a particle and an antiparticle. Normally, these pairs appear, instantly collide, and return their energy to the universe. But if a pair pops into existence precisely on the event horizon's boundary, one particle falls into the black hole. The stranded partner shoots out as escaping Hawking radiation. This exact boundary condition and the resulting radiation are named after the theoretical physicist who first conceptualized the math behind it. This tiny microscopic separation forces an unbreakable law of physics to balance the books, a rule that guarantees the black hole's eventual death. The universe strictly enforces the conservation of energy. You cannot create free energy out of nowhere, meaning the newly escaped particle has to be paid for. The black hole itself pays the penalty. For every single particle that escapes, the black hole sacrifices a microscopic fraction of its own overall mass. Logically, you might assume a supermassive black hole with a gigantic event horizon would be radiating particles constantly and evaporating away fast. The physics actually work in the exact opposite direction. The temperature of a black hole is inversely proportional to its mass. The bigger they get, the colder they become, to the point where giant black holes barely radiate anything at all. Because of this deep freeze, right now every stellar and supermassive black hole in the observable universe is actually growing. This heat map displays the ambient warmth of the cosmic microwave background, the leftover heat of the Big Bang. Because large black holes are so staggeringly cold, they absorb more energy from these background temperatures than they lose through their own slow radiation leak. These giants are trapped by their own immense scale. They cannot even begin to slowly bleed out until the rest of the universe cools down and dies first. We have to fast forward the universe. The cosmos must expand until the background temperature drops to near absolute zero. Only then does the net loss of mass begin. A black hole with the mass of our Sun takes roughly 10 to the 67th power years to evaporate. For massive galactic centers, the timeline expands exponentially. These ultra-monsters require 1 Google years, stretching out to 10 to the 1/206th. If you took every single atom in the observable universe and turned it into a grain of sand, counting all of them still wouldn't measure even a fraction of a % of that time span. By the time these evaporation cycles finish, every star is long dead. Planets have decayed into stray subatomic particles. The universe is a cold, dark, and completely featureless void. As the black hole gives up its final microscopic fraction of mass, the long, incredibly slow bleed suddenly ends. This image captures a concentrated burst of gamma radiation. In its final moments, the black hole blinks out of existence in exactly this kind of tiny, sudden flash against the dark void. Even the most indestructible object in the cosmos is eventually defeated. The relentless, invisible bleeding of quantum mechanics dismantles it across eternity.